final session of Def. I hope everyone's recovered and well rested after last night's festivities. Before we begin, there's something we have forgotten to do, which is a conference photo. So I will remind again at the end of this, the end of André's talk, but we will do that straight after this talk. It will just be outside the entrance here. So with that, it gives me great pleasure to introduce André and LeClair, who will tell us about UV completions of TTbar deformations of CFT.
All right, thank you. Okay, thank you. Okay, well, it's a pleasure to be here. Never been to Berlin, and it's been exposed to some interesting work in this vibrant community. It's my first time participating in these kinds of conferences. I was actually trying to decide what to talk on. There was two possibilities. The title's Integrability, Duality, and Deformations. So in the past year, I exchanged a lot of emails with some of your friends here, Svetos and Siampos, and they kind of helped me out on a problem I had been working on for quite a long time, which would fit under integrability and duality. The simplest integrable model is the Hagedorn model, and surprisingly, it's not fully understood, and it has a duality, but it's not clear that it's a strong to weak coupling duality, and it's not clear this analytic continuation actually makes sense. So I think a lot of people in this audience could help out with that. So that's not what I'm going to talk about, because I don't think that this issue is fully resolved. So instead, I'm going to go with integrability and deformations. Okay? No dualities. Okay. So it's based on just some recent papers I wrote last year, and more recently I collaborated with Shangrim on. This paper was just accepted in JHEP. So what is the problem? The problem is very general. Let me remind you some basic features of the renormalization group. So I'm going to formulate it in terms of an action. So I'm going to assume I'm given some conformal field theory, and then I start perturbing it with both relevant and irrelevant operators. Now, the standard law is essentially correct. If you want low energies, you can neglect the irrelevant operators. That's why they're called irrelevant. For example, in studying the standard model, we don't have to look at quantum gravity corrections. Those are all irrelevant perturbations. Okay? But if you're interested in very, very high energies, then it's the irrelevant operators that completely determine the physics, determine the ultraviolet properties of the model. Right? There's a crossover region, which I won't really be interested in. So the fundamental question is the UV theory well-defined and finite? I mean, this all beyond standard model physics is basically trying to address this question. What is the high energy theory? Is it a string theory? Is it finite? Just pure quantization of Einstein's action? We know that's not defined in the ultraviolet. So first we have to see if the UV is well-defined, and then can we reconstruct it? More interestingly, can we reconstruct the UV theory from limited information in the infrared? Okay. Like for example, we have the standard model, view that as a low energy theory. Just knowing the information that we know about the standard model, can we figure out what the ultimate UV theory is? And in general, the answer is obviously no. I mean, well, one way to formulate that is because of the c-theorem. C-theorem tells you that in the flow from the ultraviolet to the infrared, there's some degrees of freedom are lost. So we could stop here, but I'm going to provide a lot of examples where the answer is yes. Okay, we can reconstruct the UV theory. So this is central to, well, I already mentioned standard model, quantum gravity. Within the context of quantum gravity, there's a set of ideas called asymptotic safety. Like maybe, for reasons we don't fully understand yet, maybe quantum gravity, Einstein's theory secretly has some fixed point in the ultraviolet, and you don't have to worry about ultraviolet divergences if there's a conformal fixed point. And it's also connected a little bit with the swampland. Swampland, that notion was born in string theory. I mean, suppose you have a low energy theory. Does that theory come from a string theory or not? So that's essentially the same question. You know, maybe there is no ultraviolet completion of some low energy theories. Okay, in that case, it's the context of string theory. But the same ideas will apply here. So, like I said, we have to limit the scope here. So I'm going to be only in 2 dimensions. That allows integrability. Then I'm going to, so I want to look at this, the perturbation by irrelevant operators. So I'm going to the very high energy limit now. So the irrelevant operators are the important ones. I'm going to take the leading irrelevant operator to be TTbar. Many people here are familiar with this kind of thing. T and T bar are the left-right components of the stress tensors. This is a dimension 4 operator. That'll be the leading one. And then I'm going to consider adding some higher irrelevant operators. How to do that was described by Smirnov and Zamolodchikov. Essentially, if the theory is integrable, well, every theory has a stress tensor, okay? But if it's integrable, there's higher dimensional versions of the stress tensor that define local integrals of motion. Okay? So they all have integer spin. And from that, you can construct the analog of TTbar. Right? So TTbar 1 is TTbar. Okay? S here is an integer, typically an odd integer, but it depends on the model. And the dimension of these operators is 2 times S plus 1, so it's an integer. Higher and higher dimension. So this is the model I'm looking at. Some CFT, and then I'm going to perturb by all these higher TT bars. Okay. So a probe to see whether the ultraviolet is well defined is to consider the ground state energy on a circle of circumference r. In stat mech, that would be 1 over the temperature. And so the ground state energy, it's conventional to express it in terms of a scaling function, C of mr, with this coefficient. And C, well, if the theory was conformal, C would be the Virasoro central charge. Okay? But if the theory is not conformal, it tracks the RG flow. Okay, so this is a function. This should be defined in the infrared and ultraviolet. It should be defined for all scales if the theory is fully well defined. And this is kind of obvious. Infrared limit is R goes to infinity. UV is R goes to 0. Okay. So pure TT bar is very interesting, and many people in this room, I'm sure know this, but let me remind you. So I set all the higher TT bars to 0. So there's one coupling, the leading one. Then it turns out there's the ground state energy is universal. It satisfies a Burger's type differential equation. Anyway, I like to write it in this form. Okay, so here you're given, this infrared central charge as a function of the scale. Little r here is mass times big R. H is a ratio. This is dimensionless ratio here. You have that one coupling, alpha 1. And the interesting case is alpha 1 negative, so H is positive. And then eventually, if you just plot this as a function of R, you're going to hit a square root singularity. Okay. So if this is it, there's a sort of shortest possible distance. You can't go to the full ultraviolet limit. Okay. So this is the kind of picture you have. Okay. Wait, I think this is the slide I wanted. So there's 2 interpretations of this. The original TT bar, I think, was mainly the first interesting papers were in the concept of string theory. So there are, so there R star is a string scale, and that square root singularity signifies some kind of Hagedorn transition, and everything's okay. It's a string theory, okay? which is kind of an ultraviolet completion of some kind. But if you didn't know about string theory and you were just a quantum field theorist, this is not good. This is the usual folklore that if you perturb by irrelevant operators, you start generating more and more irrelevant operators. And the whole theory is out of control and it's unpredictable. Okay? So the question I posed is, can we somehow tune, so let's add all these other irrelevant operators, and can we tune these couplings to cure that singularity in such a way that the theory is fully defined in the UV? And can we actually, there's a classification problem here. Can we classify the possible UV completions? Okay. So this is the picture. So the x-axis here is 1 over r. So the infrared is 1 over r equals 0. Infrared is 1 over r is 0. That's up here. Now the leading perturbation is TTbar. So any possibility here, they all look the same around here. But depending on what the other higher irrelevant operator couplings are, these things, they start to change. And maybe there's still a singularity. But I'm interested in the ones where there's no singularity. And I'd like to classify the possibilities here. Okay.
When you say that you want to, I guess maybe you'll say, when you say that you want to tune the deformation, you mean that you want to tune the initial condition of this differential equation? So like the initial choice of operators, or you
no,
want
once you add,
particular flow?
once you add the higher irrelevant operators, you don't have this differential equation. There's no, this Berger's differential equations.
There is another flow equation.
Yeah. What I'm going to do, I'm going to use the TBA to track the RG flow.
All right. Okay.
Okay, that's going to be the main tool. Okay, so these are the steps that I would have to follow here, that we try to follow. So first, we're given the infrared conformal field theory. Okay, assume we're given that. First, you want to look at all the possible integrable relevant perturbations of this theory. Once you do that, for each of those possibilities, that determines a low energy spectrum. Okay. And you know the S-matrices. Then we turn off this relevant operator and get a massless theory. So this gives us a scattering description of the conformal field theory. We heard about this yesterday in Torelli's talk. So for each possibility here, we have a set of left-left. So L here is left, R is right. There's a set of left-left, which are equal to the right-right scattering S-matrices. It's very well known that if you only have left-left and right-right scattering, the theory is conformal. So we have a scattering description of the CFT. If there's left-right scattering, then that would break the conformal invariance. Okay, so here left-right is trivial. Now for each of these choices here, you turn on the higher irrelevant operators. This breaks the conformal invariance. So the left-right now becomes non-trivial. And it's known that it corresponds to a CDD factor. Okay, I think people know that. I forget what C stands for Castellano, but D is Dalitz and the other D is Dyson. Now, I continue the steps. Then we use the thermodynamic Bethe ansatz as the main tool. And we require that there is a well-defined central charge in the ultraviolet. So the scaling function is valid on all scales. Okay. I'm also going to require this ultraviolet central charge to be rational. It's hard to justify that exactly, but it turns out if it's rational, there's a better chance that we can identify what that conformal field theory is. All right. For example, in some cases, it seems that everything's well defined, but the UV central charge is less than 1, and it's irrational, so we can't even identify that with a minimal model. Okay, so we don't, that theory doesn't even exist. But somehow, well, I don't want to focus on that. And we're going to restrict to diagonal scalar theories, sometimes called reflectionless, meaning that if two particles, you have particles of if this signifies a particle of type A, then A scattering with B produces A and B's, not C's and D's. Okay. For example, the sine-Gordon theory, for example, is not diagonal. The solitons, there's a U1 charge, and there's a reflectionless stuff, so this is not necessarily true. So anyway, this is mainly for simplicity. Okay. So I think the most interesting example, which is the one we worked out in quite a lot of detail, is just the Ising model. It's probably the simplest conformal theory, right? And in the first step, it turns out there's two integrable perturbations. First one is kind of trivial. This is our conformal field theory. We know this has a Majorana fermion description. There's two primary fields. One would just correspond to adding a mass term. Then we set that mass to 0 to just get the conformal field theory. Then we start adding TTbar. But in any case, this is the simplest case because this is a free theory. So the left, and right, S-matrices are just -1. The minus is because it's a fermion. And well, we're going to, this case, we could definitely classify the possible ultraviolet fixed points. Kind of more interesting is that the other primary field is a spin field, and it turns out that this is also integrable, as first shown by Zamolodchikov, late 80s. And it involves 8 particles, nothing to do with the Majorana fermion. So you have 8 massive particles here related to E8. I'll explain that later. So back then, people completed the bootstrap, especially people up in Durham. And so the left, and right S-matrices are known. But they're kind of complicated, right? I mean, there's 8 particles, so there's 64 different S-matrices, but it's all known. I'm actually not going to need the exact form of these guys. So, but given those left, and right S-matrices, now we have to consider the CDD factors. This wasn't really in the literature before, not quite in this way, because, for example, Smirnov, Zamolodchikov, they were focused on the massive case. Right? So there, the CDD factors were exponential of I sinh S theta. Okay. Where these dimensionless couplings are just proportional to the original couplings. For example, G1 would be alpha 1 times m squared, which is dimensionless. Okay. But I realized early on when I was looking at this problem that you had to factorize the sinh into e to the plus s theta and e to the minus s theta and identify them with right-left versus right-left. Okay. That made the TBA converge. Okay. But anyway, if you look at this form, you can see that it satisfies this is essentially the only identity that these guys satisfy. Right? It's like a kind of unitarity relation. Mm-hmm. So, but this previous form is a little hard to work with. In general, these what's in the exponent here this doesn't converge. So I want to work on a slightly different basis, and this is based on a pretty famous paper of Alyosha Zamolodchikov. Let me consider the center mass energy for left with right scattering. So here, this theta here, so it's just m squared e to theta. This theta is the difference of the two rapidities of the two particles. And Zamolodchikov proposed this kind of form for the S matrix. we saw this also in Torelli's talk yesterday. Now, if there's many particles, it's quite straightforward to see what the generalization is. It looks like this, okay? And how the masses appear here is such that you can check that if this is pure TTbar, only the lowest one, then this reproduces the results of the Berger's differential equation, etc. So this tells you where you should put these masses. Okay? And it turns out you can match. So originally I wrote down Lagrangian in terms of these parameters alpha. You can explicitly relate those parameters to these mu's. I'm not going to give that formula, but you can definitely match these two expressions.
So those mu are satisfied some sort of triangle relation as well, or they're just fixed?
Can you repeat the question?
Those mu's,
Yeah.
do they have to satisfy some sort of triangle relation, or they're fixed just by?
There's some consistency conditions, yeah, which I'm not writing down. Because remember, we're trying to fine-tune all these alpha couplings. So that fine-tuning involves some identities, yeah, that are, they're sort of triangular. I'm not writing them down here. But we can match the two descriptions. So we can relate these parameters to the Lagrangian. So the convenient form we found, well, if you look at this particular ratio and define a beta, this is dimensionless here, then, so these CDD factors, the basic building blocks is this tanh. Okay? And depending, you could have many factors, so with different betas. So JAB here, big JAB is an integer. So that's the form of CDD factor we're going to consider. Okay, now since the equations are getting longer, I stop writing. So the TBA equations are quite well known. So this is not new. You have these so-called pseudo-energies, and they satisfy an integral equation. These big L's are log of 1 plus e to the minus epsilon. There's a left and a right one. These are the source terms, driving terms. This is just comes from the, if there's no interaction, this is just the energy, okay? And once you solve the integral equation, which you have to do numerically, okay, then there's a simple formula for the ground state energy. And from that, I can get the central charge, effective central charge, okay? So that's the main tool. These kernels are derivatives of the log of the various S-matrices. Okay, so there's two types of kernels, one for the left-left, one for the right-left, both given by minus I derivative log S. And they appear both, the left-right and the right-right appear in the integral equation. Okay, okay, so here's one example, I'm not even telling you what the spectrum and everything is. This is one example we looked at based on SU3, which is actually, this is a perturbation of the three-state Potts model. Turns out the infrared central charge is 4/5. I'm showing this because this is a plot of this L function, the log of 1 plus that. And you see how it forms a plateau here, okay? This is not quite a robust plateau. It's a different case corresponding to the maximal central charge. But nevertheless, even though there's not a plateau, you can extract the UV central charge from values of this plateau. And the formula works even if you have a profile like this. Okay. So here, I want to extract the ultraviolet central charge, if it exists. All right? So I have to look at the integrated kernels. So I'm going to, these little KABs are the integrated kernels for right and left. And then the K-hats come from the kernels for right-left. Okay, so they're not equal, right? And let me define x hat to be e to this the pseudo energy. Right? So turning on in these flat regions, the integral equation becomes algebraic. And it's a relatively simple form. Okay? So you see, if I turn off right-left scattering, this is still non-trivial. And from the solution of this equation, you can figure out the central charge. In that case, it would be the infrared central charge. Then you turn on k hat, solve the equations again that should determine the ultraviolet central charge, if there's a solution. Okay, there isn't always one. So it turns out that this tanh was useful because the integrated kernel is always 1/2, no matter what the beta is. Okay. So for each CDD factor, this k hat, well, there's big JAB of these factors. Each one gives 1/2. So k hat AB is just this. They're all half integers. Mm-hmm. And it's going to be convenient to arrange these integrated kernels into matrices, big K and k hat. So remember, this one comes from right-left scattering. This comes from the conformal theory, left-left scattering, right-right. And then there's a very nice formula for the central charge. There's a version of this formula in Alyosha Zemlyakov's paper, but we generalized it to a more general situation. This LR here is so-called Rogers dilogarithm. It's the dilogarithm, standard dilogarithm plus a log term. Okay. So it's relatively simple. So if you find the solution to these x hats, this plateau equation, you plug it in and you see if you have a sensible central charge. Okay. So before we turn to a specific model, there's some very generic cases. Okay. So it turns out if there's too many CDD factors, there's no solution. Okay. We call that the saturation point. And that's going to give you the highest possible ultraviolet central charge. Okay. And you can see it's quite easy. I mean, without even specifying the S-matrices and these matrices K, you know, if k hat set, well, let's call it k hat 0. The 0 refers to this be the saturation point. If k plus k hat is 1, then you can see that all these x hats are 0. And that's the maximal central charge, because remember, the epsilon has to be real, right? And so the lowest value it could be is minus infinity, and that's when x is 0. But you still have a non-zero ultraviolet central charge, and it turns out to be always the maximum one. Okay? So in this limit, the maximal UV central charge, turns out, I'm going to look at theories based on Lie group G. But in any case, it's quite general here. It's twice the number of particles minus the infrared central charge. It's kind of a nice formula. In the models I'm considering, based on Dinkin diagrams, the number of particles is just the rank. Okay. Another generic solution I call diagonal, where instead of this equal to 1, this is equal to 0. So now k hat is just minus k. Remember, we know k. K is given by the left and right S matrices for the conformal field theory. So those are all determined, okay? We're trying to find k hats. If you just take this very simple choice, then all the x hats are 1 instead of 0. And you still have a well-defined UV central charge. This case is just the number of particles minus the infrared central charge, which turns out to be the central charge of this coset. I'll explain this notation later. Well, GK is the Westerminer-Witten model at level K. Okay. But I'm getting a little ahead there. So let's look at the Majorana case, the fermion. Well, let's look at Ising. Try to do all of Ising. So let's start with the simple Majorana spectrum. Okay. The integral equation is quite simple because there's no left or right kernel, but there is a non-zero left-right S matrix. So here, there's only two cases. There's only two ultraviolet completions. You can have one of these CDD factors, one of those tangents, and that's the famous example of Alyosha-Zemlya-Lodrikov. This scaling function is defined everywhere. The ultraviolet central charge is 7/10, which is tricritical Ising. You can have two of these CDD factors. That's the saturation point. And that C is 3/2. Okay. And the interesting thing here is that, well, so far this is what we have. We started at 1/2, okay? One CDD factor gives you tricritical Ising. The other one is C equals 3/2. I found that last year. I didn't know what that theory was. Then talking with Shangrim An, my current collaborator, it turns out it's the super Singe-Gordon theory at the self-dual point. Okay. And the 3/2 is a central charge of one fermion plus one boson. It's also supersymmetric. So there's only two completions for the Majorana fermion, and they both have supersymmetry. I mean, that's kind of good news for the SUSY community, who loves supersymmetry. Here, we didn't put supersymmetry in. Why is the theory massless? We have a massless flow. So in the infrared, there's still something left. It's the massless Majorana fermion. And it's massless throughout, everywhere. It's always massless. But it's still not conformally invariant. So there's a UV and infrared central charge. And there, the Majorana fermion can be interpreted as a Golstino for the broken supersymmetry. That's what's keeping it massless.
So I was wondering, this identification of the UV theory, is it based only on the central charge or also some other piece of evidence?
That's a very good question. So since this is our first stab at this problem, we just checked that there's a well-defined solution to the TBA for all scales with a well-defined UV central charge. Okay. And with more work, you can, but it's hard, but it can be done. You can expand around the ultraviolet in a careful way and, for example, figure out the dimension of the relevant operator in the ultraviolet that it flows out of. Okay, so you flow out of the ultraviolet with a relevant operator. It arrives with TTbar in the infrared. But we couldn't do that for all these cases. It was too much work. We're kind of working on it now, but it's a little bit tricky.
Maybe one quick related thing. So, and this is something that I don't know even in the case of the tricritical Ising flow, which is in principle well understood since a long time. Could one in principle look at the spectrum of excited states along this flow and see that it arranges the spectrum of Ising in one point, and then it arranges the spectrum of the tricritical Ising?
To my knowledge, that hasn't been done. So what Zemlya-Lodrikov did, the best he did in his paper was that, okay, he figured out that he had the right central charge, but then he did one more expansion around the ultraviolet, and he figured out the dimension of the perturbation there. And it was what was expected. Okay. But your question is much more refined. These are kind of hard, but studyable. Okay. Okay, but that's not it for Ising, right? Because remember, there's this other description of conformal Ising with 8 particles. So I'd like to review that a little bit. So why E8? Well, after the original work of Zemlya-Lodrikov, I wrote a paper with Denis Bernard and Shangrim on essentially perturbations of all the cosets and proposed S-matrices for that. Okay, so this is going to be one special example. So I'm going to let G here, just a simply laced Lie group, AD type. Here's my notation. GK was Witten at level K, just current algebra. And then GK with this bracket, square bracket, is going to refer to this coset. Okay? Now, it's known that if this is level 1, 1, 2, which is that guy, this has diagonal S matrices. Okay? Now, let's focus on the minimal models. Okay? So what I just described in terms of Majorana is this Ising. Ising. There's one. The rank. The number of particles is the rank. SU2 is rank 1. So this is for these groups. This coset for SU3 is 3-state pods, and we did the classification from that case. There's E6, E7, which we couldn't do everything, but I'm going to focus on E8 because, interestingly, both E8 and SU2 have this coset has central charge 1/2. So they're both Isings, but in a very weird description, appropriate to a magnetic perturbation. Okay. So if I'm trying to classify UV completions, I have to consider this E8. Okay. So then it gets a little technical, but some of this is known. So let me describe the conformal description. Just the left, right S matrices. So, like I said, there's no E8 symmetry, but a lot of the structure can be figured out from the E8 Dinkin diagram. With this labeling of nodes, this is the incidence matrix. Remember, the big K are the integrated kernels. So they're known, because we know the S matrices for this guy. And it takes this form. So you have this funny matrix of integers. But this is known, okay? All right. Remember, the saturated case is K hat 0 is 2 over 2 minus I. Okay. What was I going to say? Okay. So then you start going fishing, okay? So the big K, which determines the conformal field theory, is known. And then you're trying to cook up some left-right scatterings that have a well-defined flow all the way to the ultraviolet. So it's a bit like fishing. But the constraints are that the elements of this K hat, have to be half integers, as I said before, because integrated kernel for each CDD factor, each tanh gives 1/2. So they have to be half integers. So let's look at this. So the saturation point, the K hat was just, remember, is just 1 minus K, which is 2 over 2 minus I. Okay. So that's going to give the maximum central charge. But then, since all the elements have to be half integers, you start reducing the number of CDD factors. And here, there's too many particles to do this very, very systematically. So what we did is we took K hat 0, this is the saturated one. And then we took let n be an integer, and we consider this this set of these possible left-right scattering kernels. Okay. Again, a matrix of integers. Right? The K hat 0 is this. So multiply by n over 2, you get this. So let's just check the conformal case. So if you set K hat to 0, then the UV and the infrared central charge are the same. There's no flow. It's a conformal theory. So there, if you solve the plateau equation, this algebraic equation, you get algebraic numbers. It turns out they're relatively simple. They only involve the irrational square root of 2. And kind of remarkably, if you add up, I had this formula in terms of Rogers logarithm for the central charge, and you have 8 of these guys, kind of funny values, and you get exactly 1/2. Okay. So now we're going to turn on left-right scattering. There's the lowest value. We found the lowest one. Here, this integer n is 1. Okay. Now, the solutions aren't as simple. But interestingly, like 1, so these are the values of these x hats, 8 numbers. And, well, they're supposed to be algebraic numbers, and they are. But they're roots to a quintic polynomial. Okay, so this first guy is 1 root to this polynomial. And kind of remarkably, you plug it into the Rogers-Dye logarithm formula, and you get, with these weird numbers, you get exactly 21 over 22, which is one of the minimal models. I think it's the 9th minimal model. Okay. And this case this is the analog of the Zaimolodchikov tricritical Ising to Ising. Here, because of some older work, we know what the UV CFT is. It's this E8 coset at level 2. So E8 coset at level 2 flows to E8 coset at level 1. And it's a diagonal scattering theory. Okay? And because we know something about these coset flows based on work that I did with Bernard and An, we know the dimension of the operator in the ultraviolet that pulls you out of the ultraviolet. It turns out to be 2 over 11. You can extract that with some work from the TBA. Okay. So that case, that's the analog of tricritical Ising to Ising. Okay. Saturated cases, the maximal central charge. It's not easy to guess this, but in any case, here all the x hats are 0. Here n equals 2. That's the saturated case. Turns out it gives a UV central charge of 31 over 2. Okay. And that we can identify also. It's not the coset, but it's the E8 current algebra. Westman-Witten model for E8 at level 2. It turns out that has that central charge. Diagonal case is interesting. Again, infrared is always 1/2. It turns out to be 15 halves. And this we have a proposal for what that theory is. What is this theory? We just note central charge. We believe that it's if you take the current algebra GK and you mod out by a rank of U1s, you get something referred to as a pair fermion. This is not the ZK pair fermion. It's a non-abelian pair fermion that depends on the group. Okay. So we identify that CFT as PF2. Okay. And it has that central charge. Okay. So thus far, this is what we have. We have at least 5 UV completions. And here they are. Now, are there more? Well, we kind of ran out of steam a little bit because you have this big matrix of integers, 8 by 8, and you have to start lowering these integers to lower the central charge. And if you just do a random choice, usually there's no solution and no ultraviolet completion. So that would be kind of in the swampland. Okay. I mean, the S-matrices are defined, the kernels are defined, but there's no solution to the TBA. So there's no ultraviolet completion for certain types of C to D factors. But probably we could probably write a clever program to sort that out. But we stopped here for E8. We were happy with at least 5 completions. I believe there's more. And the reason I believe there's more is because we looked at some simpler cases. Okay, so replace E8 with SU4. Okay. Now, there's only 3 particles. So it's feasible to do a classification. Remember, K is known, the S matrices are known, so the integrated left, right kernels is known. Here it is. This is the K. So, what we're going to do, remember, the K hats have to be half integers, and because of the symmetries, there's only 3 independent integers here, n1, n2, and n3. So what we did is, well, now it's not so bad. There's only 3 integers. So it's easy to scan through the possibilities because the saturation point, by the way, the infra-red central charge here is 1. Okay. But it's easy to go through this by hand, do one case at a time, because the saturation point is such that these ends can't be any larger than 2 or 3. I forget. I'll show you in the next slide. So here we scan all possibilities. Okay? Sometimes there's no solution, swampland. Okay? But the solutions we found was quite rich. And here we believe this is a complete classification for this case. Okay? And this is what we found. So here are these integers, n1, n2, n3. Okay? So if they're all 0, that's the conformal case. So CUV equals CIR is 1. This is the SU4 coset at level 1. Okay. Then we found all these cases. I guess the largest integer is 4. Okay. There's no more after this. Okay. Some of them we could identify. Some we couldn't. Okay. So let me look at this one. So this is the analog of tricyclical Ising to Ising. So again, these are irrational numbers, but they're algebraic. They're actually solutions of a cubic polynomial. But you plug it into the Rogers dialogagram formula, and you get a CUV of 11/7. And then we checked in all cases that we're not just doing the plateau equation, that we look at the actual S matrix, plug it with the actual kernels, and solve numerically the full integral equation, and see that it's a nice flow. Okay. So this we identify as a SU4 coset at level 2. Okay. Then this one is an analogous to the previous case. It's parafermion, but parafermion based on SU4. This is the diagonal case. This is called the minimal case. The other ones, we don't. Okay, the saturated case we understand. Okay, this is not the coset, but it's just SU4 West-Winwood model at level 2. So the maximal central charge here is 5. This one we believe is this coset, but we don't know yet. And some of these other numbers, the ones that are multiples of 1/5, we don't know what they are exactly. But we completely specified the S matrices. These theories exist. We just can't identify them yet. They're probably related to some subgroups of SU4. Like, for example, we're kind of guessing SU4 level 2 mod SU2 level 1. That has the right central charge here. This one too, this coset has the right central charge. The solutions to the plateau equations here are relatively simple. They just involve the golden mean compared to these other ones. Anyway, so even with 3 particles, there's something like 11 cases here, and there's still, well, we know the central charge. That's all we know is the UV central charge. We don't know exactly what these theories are. So there, you'd have to do what you were suggesting. We had to do further work around the ultraviolet, first of all, to figure out what the dimension is of the relevant operator that pulls you out of it. Then, with that, it gives you some hints of what this theory is. Okay, so there's quite a lot of work still to be done. So, summary, yeah, okay, good. Well, I think it's a well-defined classification problem. There's still work to do, but it seems well-defined. We found some results. It's interesting. This is an interesting issue. For the Majorana fermion, remember the SUSY supersymmetry was actually important because the fermion was identified as a Goldstino. This is sort of from the Goldstone theorem. That's why it was massless. Okay. For these other cases, well, again, based on some work I did a long time ago with Denis Bernard and Shangrim, it was actually in the title. There's these theories have so-called fractional supersymmetry. So there's, in general, there's in all these flows, there's a symmetry with some fractional spin currents, not 3/2, not supersymmetry, and very non-abelian, but they're known to exist. Okay, and probably there's something going on that is an analog of the Goldstone theorem for these weird symmetries, which would partly explain why the particles remain massless throughout the flow. So I think I have a little time. And so there's, I think I've already mentioned some of these open questions. Okay, so one thing, for example, what is this E8 thing? Well, suppose you had an Ising model in a magnetic field, but it was vanishingly small, and you turn on these TTbar perturbations. Maybe that has some physical applications. I already mentioned this, the role of these fractional supersymmetries. Are there more based on this E8? I believe there probably is, but we can't prove it, and we didn't systematically analyze it. Okay, thank you.
So, thank you for a very nice talk, and we already have one question, so please.
Thank you for the nice talk. First of all, concerning this classification, you were scanning positive integers. I guess that had to do with a requirement of the y functions not to go negative, perhaps, or something like that?
Well, it's basically because quite generally these the CDD factors are products of this tanh theta over 2.
All right.
Okay, so each of those tanh factors, the integrated kernel is 1/2. But remember, it's the log of the S matrix. So if you have 10 factors, then it's 10 over 2, the integrated kernel. Okay. So that was a limit there. Mm-hmm. So there had to be integers for that reason.
And related to this, if I now wanted to re-express the CDD factors in terms of the TTbar S basis, I guess I would get an infinite combination, right?
It's infinitely, it's fine-tuned, so it's infinitely constrained in a sense.
Yeah.
But we wrote the exact formula in our paper with Shangrum. But yeah, it's a strong fine-tuning.
Yeah, no, absolutely.
Yeah, it has to be in some sense, right? But yeah, you can relate these, remember these tanh, the parameter in the tanh was what I call beta, which is the ratio of the mu's to the masses. Mm-hmm. So that you can then compare with the CDD factor in, say, Smirnov-Zamolodchikov, and then you can make a connection with the Lagrangian parameters. But it's an infinite set of relations, really.
Yeah.
Right, because there's an infinite number of couplings.
Okay. We have a question at the front.
It's kind of maybe conceptual question. Did I understand correctly that you think that just TTbar deformation by itself
Can you
is
speak a bit? Is it on? But maybe just speak a bit louder into it.
Is it? Yeah. Did I understand correctly that you think that TTbar deformation by itself is ill-defined?
I think it depends what you want to do. I think for string theory applications, it's actually the right thing, right? Because they interpret it as some of the original papers, Dubovsky and these people, I know you wrote some papers too,
yeah.
We cite you, by the way. The physics is just a pure TTbar, and it has a singularity. And I think nobody's proposed anything about beyond this. It's just singularity. It's because there's some kind of string theory there. But I as far as pure quantum field theory, I would say it's not defined. Well, not defined on all scales. Or until somebody figures out how to maybe come up with some proposal for interpreting that singularity probably as maybe an instability of the vacuum. Until something like that is, which I don't think exists yet, I would say as pure quantum field theorist, I would say it's not defined. But has no UV completion. It has the smallest possible scale, so you have to stop. Then what do you do?
Do you know what happens with excited states if you
No.
consider your flow?
No, we didn't, no, that would be interesting to study these excited states, just like,
Thank you.
Maybe I can just ask, so how should I think about the fact that the possible irrelevant perturbations seem to depend on the different relevant perturbations? Is that just a tool?
it's really a tool, yeah. But it took a while to sort that out because it's a little tricky, but you have to keep it straight in your mind. See, we first imagine turning on just a relevant perturbation. And the theory is integrable, so then we in principle know the spectrum in S-matrices, okay?
Right.
Then we take a massless limit to describe the conformal theory. Okay, so essentially, in that case, you're actually turning off the relevant operator. But you see, this is the part that you have to keep straight, is that this massless limit is the UV limit, ultraviolet limit of the relevant perturbation.
Right.
Right? I mean, you take the Majorana fermion, as the mass goes to zero, that appears in the ultraviolet, right? Because at very high energies, the mass is irrelevant. Okay. But then that's a tool that we forget it, that gives us a scattering description of the conformal field theory, but then we view it as a description of the infra-red theory.
But so all of these different descriptions of the same infrared
Right.
theory, they describe the same physics at the end of the day. They are just different descriptions of the same
Yeah,
physics.
they're different descriptions of the same. Just say it's a kind of a little bit of a miracle, like this E8 coset and the SU2 coset both have central charge
But
at
you
half.
should be able to access the different UV completions from only from one description.
Right. So you turns out like for Ising, there's only two integrable perturbations. One has his E8 spectrum, one is a Majorana fermion. There's nothing else, so that's all you have to work with. For other central charges, there could be many, like a C equals 1, there could be many possible conformal theories in the infrared that have different left and right S-matrices. But the way to do it is to turn on a relevant operator to fix a spectrum, then turn it off. Yeah.
Oh, we have a question over here. Maybe it's not on.
Yeah,
I don't
yeah.
know.
Hello, thanks for the talk.
Yeah, now I can hear you. Yeah.
When you classify the SU4 case, in your coset group, in some parts, you have these question marks, like it's not fully, it's like there's an ambiguity over there. Can you elaborate on that to understand what is not why those groups are not the...
So basically, for even though there's a question mark, the TBA has a solution for all scales, and from the plateau, and we can extract one piece of information, which is the central charge. See, so there's no question mark here, okay? But if I tell you, look, there's a conformal field theory in the ultraviolet that has central charge 13/7. Then you have to do some more work here. I don't know what theory has this central charge, what this theory is, but I know it exists, and I know it's central charge, but I don't know exactly what it is. It might be some weird coset of some type, but from what we've done, we can't We don't have enough information to identify these.
And the guess is agrees dimension and something else, or is just, or is that?
Wait, you say that again?
You have some question marks, but you have some guesses, some ansatz like this, for example, SU4.
Yeah, so some of them we know.
SU3.
Yeah. So some of these we know, like this is no question mark. Okay. That one either, this no. So there's at least 5 of them here that we have no questions. We know what they are.
Okay, perfect.
Partly based on things that were kind of known. There's some conjectured flows of cosets. So, and then this matches up with the right central charges. So these are, with no question mark, were pretty solid. But the other ones, I don't know.
Okay, I think Dan has a question at the back.
So, at the beginning, you restricted to easy S-matrices where you excluded, let's say, sine Gordon or something like that.
Right, right.
Is that just to make the TBA viable, or is there some actual obstruction to this analysis in the context?
It's, first of all, we didn't even know this idea would go anywhere. You know, maybe it wasn't classifiable, and maybe there were no ultraviolet completions, so it was really for simplicity.
Okay.
But in principle, like for example, suppose you wanted to look at infrared theory that C equals 1 based on the sine Gordon spectrum, say, okay. The TBA equations are very complicated. You know, they have magnons, and they were simplified by Destri and De Vega eventually, but the TBA equations are much more complicated. So it was really just for simplicity to see if this question is interesting or not. But I think we demonstrated that it's a well-defined program. So
No,
then it's just very technical to do these non-diagonal S-matrices.
Yeah, I was just in case there was like some actual obstruction you knew about. I wanted to check. Okay.
Okay, great. I think we've had quite a few questions. We're a little bit over time. So let's first thank André for a fantastic talk again.
Thank you.